some time for maybe discussion of questions pending from HC Verma for thermodynamics. Okay. Or we have tomorrow's session also for discussion of questions. Since we have 2 lectures back to back, we can keep one of the sessions for discussion of the questions, etc. I want to get started with the concept set of heat transfer as soon as possible today, because that way then you can also start with the homework questions, etc. of heat transfer. It's a very easy chapter, and can complete it sooner and then move on in our syllabus with the next part. So the process by which heat transfers from a material or a body at higher temperature to a material or body at lower temperature till thermal equilibrium is established, that process is called heat transfer. And in general, as we know, there are 3 modes of heat transfer: conduction, convection, and radiation. So let's understand a little bit more about each mode. Conduction, it is the primary mode of heat transfer through solids. Where heat as a form of energy as vibrational kinetic energy of molecules conducts, okay, or you can say transmits from a region of higher temperature to a region of lower temperature. So that is about conduction. Now the second mode of heat transfer is convection. Convection is the primary mode of heat transfer in fluids. That is liquid and gaseous media. Wherein heat as a form of energy, which is at the molecular level, translational and rotational, kinetic energy of fluid molecules transfers from a region of higher to lower temperature through the mechanism of convection currents. So convection currents is a complex flow of fluid molecules within the volume of fluid. Due to thermal energy. So these are the two modes of heat transfer through material medium, that is solids and liquids and gases. And of course, the third mode of heat transfer, which you might have heard about, is by radiation, which does not involve any kinetic energy because it does not involve any material medium at all. It involves heat transfer through electromagnetic waves. Now, the same type of waves, electromagnetic waves, which are part of the visible light spectrum, or infrared, ultraviolet, X-rays, etc. So part of that electromagnetic spectrum. So heat as a form of energy in form of electromagnetic energy in radiations rather than in the form of kinetic energy of molecules. That type of transfer of heat is called radiation. So we'll come to that. Make a quick note of these two first. Okay, so talking about the third type of mode of heat transfer. Sorry?
1 minute.
Yeah. Okay, done.
Yes, sir.
Yes, sir.
Okay.
Sir, 1 minute. The last part is.
Last part. Okay.
Sir, what is written after the complex flow of fluid molecules?
Within the volume of the fluid. Okay, due to thermal energy. So, these currents are set up within the volume of the fluid, right? From one region to another region. Like even the ocean currents are example of convection current, right? Because of temperature range across different
Got it,
parts
sir.
of the ocean. Or if you observe liquid boiling, right, in a glass container, you will be able to clearly observe these type of convection currents which are set up.
Done, sir.
Okay. The third mode of heat transfer is called radiation. So this is the mode of heat transfer through emission or absorption of electromagnetic radiations, or what is called EM waves. So this does not involve any material particles, and heat as a form of energy is the electromagnetic energy of the waves. Okay, so by electromagnetic energy we mean the energies of electric and magnetic fields propagating through the waves. Example of this is the radiation of visible light from the surface of any body. Okay. An example of this is transmission of solar electromagnetic energy or heat from the sun's surface to planets orbiting via the propagation of electromagnetic waves through space, which is vacuum. Okay, so what is different about this third mode of heat transfer is that it does not involve the kinetic energy of any medium particles to transfer heat as a form of energy from one region to another. Rather, the heat as the form of energy is the electromagnetic energy of the waves associated with these radiations. We'll discuss more in detail about this as we go along. You have seen one instance of the understanding of electromagnetic energy, or what is called photon energy of photon. You must have studied in structure of atom in chemistry. Like when an electron makes a transition from higher energy state to lower energy state, it emits a photon which has energy equal to hc by lambda, which is the energy difference of the two levels. Or similarly, if atoms of a material come in contact with electromagnetic radiations, then an electron will absorb energy equal to the energy of a photon, hc by lambda, and make a transition from lower energy state to higher energy state. So this kind of radiation or absorption or emission or absorption of photons are nothing but packets of electromagnetic energy. They keep occurring in matter because in matter electrons exist in different energy states, and they keep making transitions based on their quantum mechanics and the probabilistic mathematics by which they are governed. So they continuously keep making transitions from lower to higher and higher to lower energy states. And the process, they are continuously emitting as well as absorbing electromagnetic radiation or photons. So that process is of heat transfer is called radiation. Can you speak a little louder, please? But I can't hear you. Not able to hear you, or you can also send a doubt on text message. Okay, so now one by one in detail we will study about conduction and radiation, whereas
Just a
convection
minute.
is, sorry.
Can you please scroll it up, please?
Yes, sir. 1 minute.
Okay, done.
Just a minute. Sir, because of the electric and magnetic fields, I mean the waves are formed, right? So, can we say that it will be a bit, I mean, some heat be generated at the same time of movement of
Can we
waves?
say that? Sorry, what, better?
Can we say that there is some amount of slight amount of heat generated while moving of waves?
See, as the waves propagate from one region to another, electromagnetic energy propagates from one region to another. You understanding better? Just like,
Yes,
for
sir.
example, when you have physical waves, like mechanical waves, like the waves on the surface of water or the waves through a string. So what is happening? A combination of kinetic and potential energy is propagating from one position to another.
Yes, sir.
So like that, in electromagnetic waves, instead of kinetic and potential energy, the type of energy that is transmitting is electromagnetic energy. That is the energy associated with electric field and magnetic field. So that energy only is the heat which is transferring from one point to another. You understanding, madam?
So, sir, there is some amount of heat involved in it.
Yes, that is the transfer of heat, right? So as that
Yeah.
electromagnetic wave is propagating through space, part of that energy gets dissipated because it's absorbed by, I mean, in vacuum that will not happen. But for example, if sun rays are propagating through the atmosphere, so as they are propagating, some of that electromagnetic energy is getting dissipated through the atmospheric particles, suspended particles, or even the molecules of gas. So their temperature is also rising. You understanding?
Yeah, got it, got it.
Whereas some of it is, let's say, incident on some surface, like on the surface of your skin. When you stand out in the sun, why your skin feels hotter? Because directly the sun's rays are transferring electromagnetic energy all the way from the surface of the sun right up to the surface of your skin. And that's how
Yeah.
the molecules at the surface of your skin, they're starting to vibrate faster now because they're getting that energy from the electromagnetic waves. And so you
Yeah.
feel that their temperatures increase. But at the same time, as those sun rays are also passing through the atmospheric air, part of the energy that they possess is getting dissipated through air also.
Yeah, fine.
So
So, sir,
if the atmosphere had not been there, then you would have received more heat from the sun.
yeah,
So
fine.
the atmosphere also acts
Yeah,
like a shield for you to a certain extent. Yes.
yeah. So, at the time of tsunami, can we say that more amount of heat is generated?
So tsunami is basically bit of more because of the effect of tsunami is not like tidal waves. So it is not really affected by celestial bodies. Tidal waves, for example, are affected by the moon's gravitational field, and not to do with heat energy, but they have to do with gravitation. But tsunami is created basically when, from my understanding, tsunami is created when there is shock waves at the bottom surface of the ocean. At the ocean floor, if there is volcanic activity or tectonic plates which are crashing against each other, and that is creating shock waves, then that creates mechanical waves at the surface of water which are of huge amplitude.
Yeah, right.
You understanding the point? So
Yeah, 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 yeah.
tsunami is more about ocean waves, which are basically transverse mechanical waves, not so much about electromagnetic waves.
Okay, all right, all right. So, the tidal waves are electromagnetic waves.
No, tidal waves are also like ocean waves only, na? So they are basically mechanical waves. But tidal waves में क्या होता है? What activates the waves? It is the extreme gravitational field of the moon. As in its orbital path, it comes closer to the Earth in certain positions, right?
Yeah. So, sir, which are the waves that are electromagnetic?
Light is electromagnetic wave, beta. Light
Okay,
is
all right, all
electromagnetic.
right. No, I mean, is some kind of water wave that is being, I mean, the
Okay, so
wave of the
see,
water.
uh,
Something.
waves on the surface of water is mechanical wave. It is not water wave. But at the same time, water molecules, like molecules of all other matter, are constantly interacting with the environment through radiation. So just like the surface of the table that you're seeing, or the color of the shirt that I'm wearing, the fact that you can see the color is because there is some radiation happening from it.
Yeah, yeah,
Okay, so that kind of exchange of radiation is always happening between matter and its environment. So even the
yeah,
surface of the ocean is continuously both emitting as well as absorbing electromagnetic waves. Okay. But the so-called ocean waves are not electromagnetic waves. They are mechanical waves which are on the surface of the liquid, and they are able to propagate because the surface of uh, water or any fluid for that matter has a property called surface tension, which means it
Yeah.
has a certain kind of elasticity. No. So just like if you take a rubber membrane and stretch it out, no, it's elastic in nature. So now if you create a disturbance at some point, the entire rubber membrane will vibrate up and down.
Yes, sir, it will.
So that the surface of any liquid also has that similar kind of property of elasticity. It is called
Yeah.
surface tension. In fact, we'll be studying about it in the chapter properties of matter later. So it is that surface tension property of elasticity which enables waves to propagate through the surface of any liquid.
Okay. All right.
Understood? Then another form of mechanical waves is sound waves, which passes through matter. So for example, sound waves can propagate through the volume of a liquid or through gases or even through solids. So they are basically pressure waves. They are also mechanical waves in nature. They create vibration of molecules.
Yes, sir. Thank you.
So, I mean, basically, we say that wave phenomena can be divided into two categories, mechanical waves and electromagnetic waves. So, mechanical waves involve mechanical energy of medium particles, vibration of medium particles, and the energy propagation is in the form of mechanical energy. So, it's a combination of kinetic energy because of motion and potential energy because of the alternate compression and rarefaction of the material of the medium. Whereas electromagnetic waves does not involve any matter. It is basically electromagnetic energy in the form of photons, which are propagating from point to point. Just like visible light is an example of electromagnetic waves, but so is infrared or ultraviolet or X-rays or gamma rays and so on and so forth. Cosmic rays, radio waves, so many microwaves, so many different examples. Okay. And further mechanical waves, when we study that chapter, we'll see that it's divided into two categories, transverse waves and longitudinal waves. Okay. Okay, now as I was saying, in this chapter of heat transfer, we will be studying two of these three phenomena in detail, and that is conduction and radiation. Whereas convection, we will not really be studying as part of our syllabus so much. And when I come to that, I'll explain why. Because convection is a much more complex phenomena, which cannot be described by simple physical laws, but it has to be described by very complex simulation, computer programming based simulation. So that kind of study is not possible at 10+2 level. In certain branches of engineering, it is undertaken in a lot of detail, like mechanical engineering, etc. Aerospace engineering, mechanical engineering, etc. So convection will just be a sort of qualitative idea for us that what is convection? Okay, it is the transfer of heat through the setup of convection currents through a fluid, but nothing more than that, no maths equations, etc. Whereas conduction and radiation we'll be studying in more detail. Before I go on, I'll just go through the messages. Anuj has sent a message that rays are sent in space to hopefully communicate with aliens. Yes, we do send radio waves that go through deep space, and they are sent in various different forms of communication, like audio waves embedded in radio signals or Morse code or various different types of signals that they've developed, hopefully to discover some kind of intelligent life form. But nothing has been officially published in regard to any positive response till date. But yes, those signals are also sent into space through what is called radio waves, and radio waves are also a form of electromagnetic waves. So not just those kind of waves, but for example, you know, space programs that involve some kind of space vehicle going into deep space, like you might have heard of the Voyager programs and Mangalyaan from India, etc. So when any instruction has to be sent from the Earth's, you know, uh, this thing, the ground station for the space mission, right up to the space probe or the space vehicle, it is sent through radio waves, which transmit through space. So radio waves are able to transmit through space because they are electromagnetic in nature. So they don't require any material medium.
So,
Hope that answers your question, Anuj.
yeah. Sir, in early 2010, a similar ray was received by that receiver, and which was decoded as wow. So, was it an answer or the ray had reflected or something?
Uh, well, I don't know. I mean, there has been like no major research that has pointed out till date that there is actually some like possible alien life form, or there are many people who believe that there has been research, but it is not publicly published. That research, it is not made available to the general public for whatever reasons. So I unfortunately really don't know the answer to your question. But from my understanding of science, like there is next to zero probability that there is any alien life form that we can actually communicate with. Even if there is, then the probability that it is anywhere near us in such a way that we'll ever be able to communicate is very, very low. So while it is part of science fiction and all that, but it's almost impossible that there will ever be any kind of contact with so-called intelligent alien life form. There might be a situation where we might see organic life in some planet or some comet that is visiting us in the form of bacteria and algae and all those things. But to actually have another intelligent life form which will be able to communicate with us the way we know communication, that is impossible, I feel.
Sir,
It
then
can be possible with future technologies.
Sorry, come again, Vita?
So it can be possible with the future technologies.
Yeah, the thing is, it can be possible, but then see, future technology, when it reaches that stage, that we can reach much further, no? Because right now there is the problem of the uh, speed of light barrier, no? We cannot travel faster than the speed of light. So unless those kind of science fiction things like wormholes and all that come into reality, warp transmission and wormholes, where we are able to bend space and time in such a way that we can travel faster than the speed of light, it's very unlikely that we can reach anywhere near other galaxies, or at least within other star systems within our own galaxy that are that far away. So it's very much part of fiction and not any kind of current scientific truth that we will be able to make contact with aliens or anything like that.
So, but Stephen Hawking had warned the space agencies against this, and he had said that if we accidentally communicate with any other alien civilization, we don't know that how much strong it might be than us. So it
Yeah,
might
of course.
attack us or something like that.
Yeah, all that truth is there, because see, everything is like, see, whatever is unknown, science cannot give you an answer for that today. Only when science reaches a point where it becomes part of the known realm, then only science can give you the answer. But what is not known to us, like, there is a probability of anything, no? So it can be that there's an alien life form that is much more advanced to us, but at the same time there's also a probability that it's much less advanced to us. There's a probability that it can be hostile towards us, but at the same time there can also be a probability that it will, instead of being hostile, it will be fearful of us. So these are all like huge unknown things until and unless science reaches that stage. But this much I can tell you, that as of today we know enough about cosmology and astrophysics to understand that uh,
So your audience,
excuse me, sir, you aren't audible. Hello, sir. Excuse me, sir.
internet issue.
Sir is not speaking anything.
Arvindo, we all know sir is not speaking. Have patience, bro.
Really?
yeah, sorry, I had got disconnected. So we were having an interesting discussion, but unfortunately I got disconnected. Now we can. So yeah, anyway, the point I was trying to make forward to you that, based on the current science, there are a lot of things that we cannot be sure of. So we don't know. So there is no answer to the question that whether there are aliens or not. Like, there is no proof that there are no aliens. I can tell you this much. While there is no proof that there are aliens, but there is no proof to the contrary also. So there is no reason why we can say for sure that no, there is no alien life form. Definitely, it's possible there is alien life form, but then at the same time, there is no concrete proof that there is alien life form also. Whereas the other thing that science, the existing technology and science can tell you that if there is alien life form, then we are not going to be in a position to come in contact with alien life form for at least a good century or so, or maybe even more.
So, but the E750B and D planets that were found by NASA,
Yeah,
they told that some conditions are ideal that can produce life or something.
yeah. So what they mean by that can produce life, there can be organic life. So for example, there is a possibility that there will be bacteria, there will be, there will be single cell organisms, or there might even be vegetation. But vegetation is also very unlikely. You're understanding the point?
Yes.
And see, as of now, we don't even know what they mean by saying that there might be form of life. Like for us, like on our planet, by life, we mean carbon-based organic life forms. But there might be silicon-based organic life forms. There might be some other kind of elements altogether. The periodic table is only limited to what we know today. So like all these other possibilities are there.
So, in
Yes.
2024, the NASA is sending some astronauts to Mars in
Hmm.
order to live there. So, how will they complete that oxygen supply for lifetime?
Oh, they will. So they will have to have a complete oxygen manufacturing mechanism for that, because Mars is this thing, atmosphere. It does not have any oxygen at all, and in fact, it has a lot of sulfur dioxide, etc., which is very poisonous. So they will have to be completely isolated in their environment. Okay, whether that is at the space station level or with the space suits that they use to move around in Mars, and they will develop a method of production of oxygen and maintaining that oxygen rich atmospheric environment artificially. Just like even today, like in within satellites and space stations, etc., there is a whole oxygen manufacturing mechanism by which they are able to maintain an atmospheric both pressure and oxygen conditions within the space station. So something like that they are planning for us.
So, but like humans inhale oxygen and exhale carbon dioxide. So
Yeah,
it can be possible that the aliens present, they do not inhale the same gas or exhale
yeah,
the
yeah,
same gas.
absolutely,
So
it is
how can
possible.
we rule out a planet by saying that it can't inhibit life?
No, we cannot rule out. That's what I'm saying. That we cannot rule out. So there might be some other form of this thing, other form of life in Mars. Okay. But the thing is, see, the probability that that life form will be intelligent just by laws of mathematics alone, the probability of that. See, you have to understand one thing. Like in the grand scheme of things, of like if you go back to Big Bang theory and when the universe was born and all that, the mechanism by which life started on Earth, because like how a planet is born, it is born, because of basically the whole solar system for a star is born out of emission that happens from the star. Okay, and materials from the core are ejected from it, but as they go into orbit around, they gradually cool down, and so there's a whole physical process involved in that. Now, in that physical process, in certain cases, the environment within those planets uh, evolves in such a way that it is conducive to life, what we call life. Okay, so there is a certain mixture of conditions in terms of the amount of gravity that the planet has, the atmospheric condition that it's atmospheric and temperature conditions and things like that. Now, then it comes down all to the chemistry of that particular planet. That what kind of elements and compounds are in abundance in the core of the planet, at the surface of the planet, and in the atmospheric gases. But even after that, for life to actually evolve, there are certain processes that we don't even understand in science today. and those processes happen by chance. It's a matter of probability. So what science has established is that in this whole process of planet making and creation of solar systems and all that, the probability that the conditions will be right for this type of life form to evolve is very, very small. And compared to that, the probability of dead planets where there is no life, the type of planets that we know like Mercury, Venus, etc., is much, much more. So the probability that even on Mars, that is so close to us, the same kind of processes would have replicated like they've replicated on Earth. And further, the same type of biological processes would also be replicated where intelligent life form would evolve over the centuries. That is like next to impossible. It's so improbable that it's next to impossible. Yeah, Diti, to answer your question, beta, electromagnetic field on the sun surface affect the formation and movement of sunspots on the sun? Absolutely, yes. Okay, solar flares, sunspots, then solar storms, so-called, which are basically uh, like hyperactive radiation events that occur from the sun's surface. These are all part of the process of electromagnetic radiation, and electromagnetic field associated with the extreme nuclear reactions which are happening at the core of the sun. Any star's source of energy, as you know, is the nuclear reactions, the nuclear fusion reactions that are happening at the core. And those fusion reactions cause very, very high amount of energy production. And part of that energy production is in the form of electromagnetic radiations that happen from the surface. So solar flares, solar spots, etc., these are all a function of that electromagnetic spectrum that is created because of the nuclear reaction which is happening at the core of the sun. Hope that answers your question.
Excuse
And
me,
Tej,
sir.
to answer your question, yes, telescopes also use radiation. So, for example, there are different types of telescopes. There are optical telescopes, there are radio telescopes. So, radio telescopes use the electromagnetic waves in the spectrum, in the part of the spectrum which is called the radio wave spectrums, okay, to discover and basically try and understand things in very far off places in the universe. Okay.
Excuse me, sir. Sir,
Yes.
how did I mean people say that the aliens are living in Mars? I mean, not they are not why only Mars? I mean, because they are not mentioning Mercury nor Venus or any other planet, but why especially
No,
Mars?
that is only a matter of fiction, beta. And because Mars is the only other planet in the solar system which has an atmosphere, no, beta.
Okay,
While its atmosphere does not have oxygen, but it has an atmosphere. And also the gravity on the surface of Mars is also kind of comparable to gravitation on the surface of Earth.
okay.
And for example, if you compare to planets like Mercury and Venus, etc., their surface temperature is too high. No? Like even metals will melt on that surface. Okay. Now, of course, you might say that why can't there be an alien life form which is made of some completely other matter, which is able to withstand that temperature? But then, like that is biologically going to be completely different. So the probability that there can be evolution of that kind of a biological system that can withstand that kind of temperature is very, very slim. No? It's much more unlikely that there is no such biological system over there.
So,
We
Sir,
understood the point.
yeah, sir, but uh, be okay, all right, you go.
And the other
so
thing is, see, what is definition of life also? No? It's limited to what we know. No? For example, according to our science, there are a lot of objects which are inanimate. Like you look at a piece of concrete or a block of wood, and we think that, I mean, a block of dead wood, and we think that there's no life in it. But actually, is there any proof there is no life in it? There's
You
no
go ahead.
scientific proof in that sense that there's no life in it. Yeah, certain parameters we might define that, okay, that if there is no growth in it, that there's no cell division, etc. But those are parameters defined by our science only, no?
Yeah, sir. These many years have been passed after people saying that there is there are aliens in Mars. But until now, the people, if we would send send some kind of satellite or something in Mars, then definitely people will get to know that whether there is some alien form or not. I mean, if not ISRO, then NASA would have definitely researched about
They
it,
have
right?
research, but again, the thing is that the research is according to the science we know, no? So there is no proof in that sense that there is something beyond that science which you're not able to understand. You're getting my point? Like there might be a life form in Mars which is completely different. Right? It might be an underground life form, and the whole the whole dimension of it is different. Like if you compare let's say bacteria cultures to human beings, there's a whole difference in order of magnitude. No? So with a naked eye, can you see bacteria cultures? No, you cannot. No?
No.
But with certain instruments, you are able to detect bacteria cultures, microscope and all that. Okay. But then what is to say that life is only limited to that which you can see through a microscope or something like that? And there might be something which is different, for which you need a different technology to detect it even. You understanding my point, Beta?
Yeah, got it.
Okay, so it is all a matter of what we can see through our technology. We are only as good as our technology, no? So there is nothing to prove that there is no life. That's what I'm saying. While we have no proof that there is life on Mars or Venus or out there in the galaxy somewhere, there is no proof till date. There has been no proof that there is intelligent life. But at the same time, there is no proof that there is not intelligent life also. You understanding my point?
Yes.
So both the outcomes are
Got it.
possible. But yes, if going by the logic that we can develop scientifically based on all the experiments we've done till now, all the observations we've done for so many decades through space probes, through telescopes, through messages that we have sent, messages that we are constantly receiving through cosmic waves, we analyze them. So the data doesn't point to any such probability being very strong. Currently, the data does not point to any such probability being strong. Okay. So I think we'll leave the discussion on this over here because this is a very interesting topic and we can go on. But the thing is like, yeah, tell me.
Sir, Mission Mangal was completed in 2014. Before
Yes.
that, also we had the pictures of the planet and some probable things that might be out of the planet. So those pictures were obtained by a telescope, right?
Yes, yes.
So
There are
just by
many
seeing
different type of telescopes. Like there are orbiting telescopes. You might have you heard of Hubble Space Telescope?
yes, sir. Yes, sir.
So that gives some of the best, best pictures, etc. Okay.
So by just looking at the picture of a planet, how can we means get that information that whether it has that atmosphere which is suitable for life?
No. We don't look at just the picture of the planet. There is, see, astrophysics is something very complex. Like if you research about it, now you will come to know. Like there are different things. Like we do spectral analysis from the radiations that come from planets. So from that spectral analysis, we get this spectral signature of the different compounds and elements that are present. In chemistry, you've studied a little bit about this thing, the radiation spectrum. Like Lyman series, Balmer series, etc. Spectral analysis you studied now.
Yes, sir.
So every element on the periodic table, it has a particular signature in terms of the radiation the spectrum of radiation that is emitted from it. So by studying such things, then by studying things like Doppler shift of light, which is reflected by bodies. So various different things like this. There are very complex techniques by which we can analyze the chemistry of any particular heavenly body also. So,
Sir,
but this is not simple stuff, and like it's like you really need to study a lot of physics and chemistry and combination of these things, how they're applied in astrophysics to understand them in full detail. Okay, so yeah, it's
sir,
good that we have had a discussion that is a little bit further away from our topic for a while.
One
It's
last,
nice
one
thing.
last.
Okay, but now I would get back to the particular topic we have, which is heat transfer. If any of you have an interest in this kind of thing like astrophysics and cosmology, etc., you can drop me a message later and I will point you to some sources from which you can read in your free time as a hobby or as an interest. Okay, but again, yeah, tell me.
So, in school, we were taught that below the Earth's surface, there are layers like crust, mantle, etc. Like crust, mantle, and core. So,
Yeah.
but in Russia, nearly in 1900s, when late 1980s or sometime, when the scientists were trying to dig a tunnel underground, the maximum they had finished nearly 12 to 13 kilometers, and the digging equipment started melting. The heat had increased so much. So how can we be so sure about those layers that there is not something else but only those layers?
Oh, that is again based on various different techniques, including the reflection of high intensity sound waves that happens from the different layers of the Earth's surface. You understanding?
Yes, sir. And people living near that area later they also reported that some unusual and strange sounds were heard during night time from that area. And later in 2000, nearly 2000, that tunnel was sealed by the government.
Yeah, so there are a lot of such isolated freak events that happen, which at the moment science might not able to explain completely. Okay, but as technology evolves and as more investigation is done into it, we'll come to know more about it, right?
Sir, and that pyramid of Giza, when those three pyramids are seen in a line from up the and you like join them in a line and try extending that line to the North Pole, it just means the time in which they would have been built. They, if you had extended that line, it would have straight met to the North Pole. So how is that possible? Means nearly 4,000 years ago.
See, about the pyramids, there are more myths than facts. So I don't really want to go into the the different predictions and the different things that people have said related to pyramids, etc. There are so many theories that pyramids could not have been built by human life forms. But the fact is, it is so ancient in our history, and there is no record of technology at that point of time in terms of historical texts, etc. So there is no reliable source of information to tell us exactly how the pyramids were built. So your guess is as good as mine. That's all I will say. We can keep on making theories about pyramids, and it might be an interesting intellectual exercise to make theories about pyramids. But there are only certain things that can be proved on the basis of what we have today in terms of the archaeological evidence from the pyramids. And on the basis of that, whatever can be proved that has been published in science, the rest is all fiction. That's all I can say about the pyramids. Okay, Vita?
So once the researchers had tried sending a drone camera into the pyramid, and it just sent an image, and then it automatically got shut. That drone automatically it just cut off. So and after that, the government banned all the researches with respect to that pyramid. So was the government trying to hide something or what?
No comments. I can't say. But most likely that whatever you have heard about such strange kind of phenomena, they are either some kind of coincidence, or they might even be somebody trying to unscrupulously try to prove something that is not true. Okay, that's all I can say.
And so it was said that those were built for mummies, but no mummy bodies have been found. Neither the king's mummy was found in the king's chamber nor the queen in the queen's chamber. So why was it built?
I have no idea, but I am not an expert on archaeology and on pyramids in particular. Okay. If you have some particular material based on this, you can send it to me and I can try and find out some information for you and point you in the right direction. Okay.
Okay, sir. I will.
Okay. Now coming back to conduction. Okay. So as I said that as part of heat transfer, we will be studying conduction and radiation in somewhat detail, whereas convection is not something that we'll be studying as part of our 10+2 syllabus. Convection is something far more complex. So it has to be studied with some computer-based modeling methods, which you might or might not learn in engineering, depending on which branch of engineering you end up with. So let's start with conduction anyhow. So as we saw, conduction is the primary process of heat transfer in a solid material. So thinking from an experimental point of view, if we have something like this, that we have, let's say, a metallic rod, like a metallic cylinder, which is made of isotropic material. That means it is made of metal which is homogeneous. It is not like a mixture of metals which is varying in property from position to position. Like it might be a solid copper rod or a solid steel rod, where the grade of copper is the same everywhere. So it's homogeneous. So something like that. So if we were to do that, okay, so we have a solid conducting object, typically a metallic rod. So why we are selecting a metallic rod as an example over here, Because metal is a good conductor of heat. Again, metals are good conductors of heat because of their phenomena of free electrons. The same reason why they are good conductors of electricity, they're also good conductors of heat, because the free electrons can be easily set into vibrational motion because they're not too rigidly attached to their atoms by any kind of by any kind of valency, you can say, or any kind of bond between the nucleus and the electrons. So they are good conductors of heat comparatively compared to non-metals. So it is convenient to think of a heat conduction experiment involving a metallic object as the conductor. So this is what we will call as the heat conductor. Now, if we are doing an experiment where what we do is we subject one end of the rod to one insulated environment, which is kept at constant temperature T1, and the other end is kept inside another insulated environment, which is kept at constant temperature T2. And T1 is different from T2. So there is some kind of insulation that we have created here. And these insulated boxes, you can say, they are called constant temperature reservoirs. Okay. So they are maintained at constant temperatures T1 and T2. So T1 is greater than T2. And also one more important part of our experiment here is that there is also some kind of insulation on the outside surface of the metallic conductor, on the outside surface of the metallic rod, so that heat cannot escape by radiation from the surface. Heat only conducts along the length of the rod. So this is insulation. There is also some kind of insulation. So at an everyday level, for example, we could insulate the rod by just packing it with some combination of asbestos and thermocol, etc. from outside. And we could create constant temperature reservoirs. For example, here we could be passing steam at 100 degrees. And we're continuously passing steam by boiling water somewhere near over here, so that maintains the temperature of this at 100 degrees C. Whereas we could have packed this region with ice, and as the ice melts, we keep replacing it with fresh ice. So melting ice at atmospheric pressure will be at a constant temperature of 0 degrees C. So that would be one way of maintaining constant temperature reservoirs. So if we do this, we will see that there is a constant rate at which heat conducts from the higher temperature end to the lower temperature end of the rod. And given that the rod has a cross-sectional area A, and a total length L. So experimentally, what is observed is that, so this is the experimental observation. If a heat conductor in the form of, in the above example, we have taken a metallic rod of isotropic physical properties. So that means it is homogeneous. It is of homogeneous material and uniform cross section. A and length L is maintained with its ends at uniform, or we can say at constant temperatures. We maintain the ends of the conductor at constant temperatures T1 and T2, such that T1 is greater than T2. Then the rate of heat conduction that is delta Q by delta T, where delta Q is the amount of heat going from one end to the other end by conduction in joules, and delta T is time in seconds. This is directly proportional to the area of cross section, inversely proportional to the length, and directly proportional to the temperature difference. So this is the experimental observation, that if we do all this, that we have a heat conductor which is made of homogeneous material, so it is isotropic in physical properties. Okay, and we maintain the two ends at constant temperatures T1 and T2, where T1 is greater than T2, and it has a uniform cross-sectional area A and a length L, then the rate at which heat will transfer from the end at higher temperature to the rate at to the end at lower temperature, that rate delta Q by delta T will depend on its properties by this parameter. That it will be directly proportional to the area of cross section, inversely proportional to the length, and directly proportional to the temperature difference. Okay. Just make a note of this statement first, then we'll understand in more detail about heat transfer. Okay, now the constant of proportionality.
Sir. 2 minutes.
Okay, okay. Finish writing. Okay, now the constant of proportionality here, that is a material property, and that is called the thermal conductivity of the material. So delta Q by delta T is equal to this constant of proportionality K, which is called thermal conductivity. So it is a material property for the heat conductor. So K is measured in watts per meter Kelvin, because delta Q by delta T is in joule per second. or watts. Area is in meter square, length is in meter, and temperature difference is in Kelvin. So from that, you'll understand the unit of this. Okay. So metals have thermal conductivity of the order of magnitude 10 raised to power 2 watts per meter Kelvin. This is an example I'm giving that you wanted to memorize this value.
Sir, the screen isn't visible.
Yeah, just a minute. I had got disconnected again. Yeah, should be there again.
Yeah, fine.
Just for example, thermal conductivity of copper is 398 watts per meter Kelvin. Thermal conductivity of gold is 315 watts per meter Kelvin. Aluminium is about, you don't need to memorize these values. I'm just giving you some examples. It's about 250 watts per meter Kelvin. Whereas, for example, if you take non-conductors like aluminium, thermal conductivity of concrete is about 0.15 watts per meter Kelvin. So it hardly conducts heat compared to all these things. Chalk, that has a thermal conductivity about 0.09. So these kind of things are typically called insulators of heat. They hardly conduct.
So what are they called? So
Yes,
can you repeat you told they are called?
not able to hear you better. Can you speak louder?
So you told something that they are called insulating.
Ah, Because the thermal conductivity is much smaller, na? Much less compared to metals.
What
Metals
are they
are
called? That I didn't know.
heat insulators, beta. Heat insulators.
Okay.
Poor conductors or heat insulators.
Okay. So heat insulators, these five which you have written.
Sorry?
So these five which you have written are heat insulators.
No, not these five, beta. You can see the metals are having very large heat conductivity. These are conductors of
The
heat.
concrete and so on.
These are conductors. They are good conductors of heat because the order of magnitude is more than 10 raised power 2. Okay, whereas these are poor conductors. Or another word for them is insulators. But here we are not talking about conductors of electricity. We are talking about conductors of heat.
Got it.
To answer your question, beta, perfectly zero, no material will have conductivity. Okay, because there is some kind of vibrational kinetic energy for all molecules, right? All materials. But yeah, for example, radon gas at extremely low density will have an even smaller value of conductivity, which if you approximate up to third place of decimal will come out to be 0.001.
So what?
Okay, so now let's come back to the equation of heat conduction. So the first thing we need to understand is a heat conductor in something called steady state. When
Sir,
we
can you scroll once?
not finish writing that part, okay.
Sir, only.
Okay, done.
Yes, sir.
Okay. Yeah, so coming back to this, a conductor at steady state. Let's understand what this term means. So basically, see, when you subject a heat conductor to the condition that I told you earlier, that you are keeping the two ends at constant temperatures T1 and T2, while keeping the outside surface of it insulated. So heat cannot escape from this. So maintaining this at a constant temperature of T1, and similarly this side you are maintaining at constant temperature T2 by creating some kind of a temperature reservoir. So this is the higher temperature T1, this is the lower temperature T2. Now, what will happen is that if you consider different points in the metallic rod, okay, like let's say we have this point A, this point B, this point C, this point D, and let's say this is kept at temperature 100 degrees C, this is kept at temperature 0 degrees C. Now, what would have happened is before starting the experiment, initially, before the conductor is placed between the temperature reservoirs T1 and T2, it would have been uniform temperature. It would have been at a uniform temperature of atmospheric temperature, let's say 27 degrees C. So temperature of all these points would have been equal to that uniform atmospheric temperature T0. Okay, but after placing it between the reservoirs, okay, when placed with one end at T1 100 degrees C and other end at T2 0 degrees C, what happens is that the temperature at some of the points, like for example in my above diagram A, B, these 2 points temperature starts increasing with time. Okay. And other points, like for example D, which is closer to the cooler end, it starts decreasing. Until after a certain amount of time, the temperatures at all points stabilize. Okay. Or become steady. Okay. For example, the temperature of the point A might stabilize to 70 degrees. The temperature of the point B might stabilize to 50 degrees. The temperature at C might stabilize to, let's say, 20 degrees. The temperature at D might stabilize to become 5 degrees. Okay. Similarly, the point which is right at the end of the rod, its temperature will stabilize to 0 degrees C. The end which is right at this end of the rod, which is at 100 degrees C reservoir, that will stabilize to 100 degrees. So that is what we mean by saying that they stabilize. Now, obviously, the temperatures at these different points will not be same. So it will not be a uniform temperature. But the value of temperature at each point on the cross section becomes uniform with respect to time or stabilizes with respect to time. So when that happens, okay, we say that the rod has reached has achieved what we call a steady state. Okay, of heat conduction. So what we mean by steady state of heat conduction, okay, that is such that a uniform rate of heat conduction exists at every position in the conductor. So I'll explain what these mean in each. Okay, so delta Q by delta T is uniform all across the length of the rod. Okay, and the other thing is that what we've discussed here. Second thing that happens in steady state is that every point's temperature is steady or stable with respect to time. Okay. So this is the definition of steady state. Just make a note of this point first. Now see, you need not note in a lot of detail word for word. What I'm saying is understand this definition and write down the keywords, because anyway I'll be sending you the notes, so you can, and plus all these things, the theory part is there in a lot of detail in your module as well as in HC Verma or NCRT, whichever you choose to follow. Just make sure you understand the concept over here and note down the key points. The key points here is that at steady state, okay, what will happen is that the temperature at all points inside the rod will stabilize. They'll become steady with respect to time. And that also means that there will be a uniform rate of heat conduction throughout the length of the rod. At every point in the rod, there will be a uniform heat current. So steady state can be described by certain mathematical equations, and we are coming to that next. Okay, so let's understand.
Excuse me, sir. Just a
Yeah,
you're right.
yeah, I told you just write the essential things. You don't need to write everything in detail. Be a little faster. Yeah, okay. So what happens is that therefore at steady state, we have a uniform heat current of this. So what we mean by uniform heat current is that within the conductor, uh, two ends are being maintained at temperatures T1 and T2. Whether we consider the rate of heat conduction through here or through any other cross section, at any cross section, the rate at which heat is conducting from one side of the cross section to the other, it will be a uniform heat current. Okay. And the other thing is that at any point, the temperature, let's say this point is P, so the temperature at the point P will be something in between T1 and T2. But at all points, the temperature is steady. So this also means that, so this is the first mathematical equation. Now the second point, it also means that there is a uniform temperature gradient. And what we mean by temperature gradient is now, if we consider at this point the temperature is T, suppose here the temperature is T, but here the temperature is T minus delta T. Because obviously T1 I have considered to be greater than T2. So temperature is decreasing. Now if the distance between these two cross sections is delta X. So as you're going from here to here, the temperature drop is of delta T by delta X. So that temperature gradient, rate of change of temperature with respect to position, that is also uniform. And that is equal to T1 minus T2 divided by length, where L is the total length of the rod. So not only do we have a uniform heat current, which is given by this formula, we also have a uniform temperature gradient. That means if we compare any 2 points which are at a distance of delta X along the length, then the temperature difference divided by the position difference, delta T by delta X, is equal to the overall temperature difference T1 minus T2 divided by the
Sir,
overall length L. So this is the second equation that is
sir,
associated, yeah, with steady state.
Sir, the uniform heat current formula Ka by L T1 minus.
T2,
Okay, sir.
T1 minus T2. The same formula we had written earlier. That one. So these are the two properties that we see at steady state. Okay, so let's understand with an example now.
Done. Sir, can you please scroll it just for a second?
Yeah, I'll just put up the example, then I'll take you back to that. So we have a solid metallic rod. It has, the metal is of thermal conductivity 250 watts per meter Kelvin. The cross sectional area is 10 centimeters square, whereas the length is 5 meters. Now what we are doing is we are insulating it from outside as usual. This is insulation, and we are keeping these two ends subjected to uniform temperature reservoirs T1 and T2. So T1 equal to 150 degrees C and T2 equal to minus 30 degrees C are maintained constant. So first of all, find the rate of heat conduction at steady state. And secondly, if we select some point inside the rod, which is at a distance of x, for a point P at x equal to, let us say, 2 meters, find the temperature at steady state. These two things we want to work out. So just try out this question. You just apply the formula that you've seen above. Okay. Okay, very good. Let's confirm the calculations. So 9 watts and
Just a
78 degrees is. Sorry, beta, come again.
Just a minute, sir.
Sorry, Anuj, I could not hear you, beta. Can you speak louder?
Can you wait for a minute?
Yeah, sure.
So done.
Okay.
Done, sir.
Yes. Yeah, so you will see that here, the first part, you have to just substitute in the formula. Delta Q by delta T is Ke by L into temperature difference. So just substitute everything in SI unit. K is already given in SI unit. But area you will have to convert to 10 into 10 raised power minus 4 meter square. So that will become 10 raised power minus 3 divided by length is also in SI unit. Okay. Into this temperature difference, which will become, now you don't need to convert in Kelvin because temperature difference in degree C is the same as the temperature difference in Kelvin. So 150 minus 30, that is 180 degrees C. Now a temperature difference of 180 degrees C is the same thing as the temperature difference of 180 Kelvin. So this will give us in joules per second or watts. So that's 5 into 1.8 into 10 raised power
90 watts per second. Meter Kelvin.
Yeah. So 10 raised power 0 हो जाएगा because yeah. So this will be your answer. Okay, where is the second part? Now we'll use the concept of temperature gradient. Delta T by delta X is equal to T1 minus T2 by L. So this T1 is 150, T2 is minus 30. The length was equal to 5 meters. Now this point we are considering at a distance of X. So when we apply this, we can see that T1 minus temperature at P divided by X should be equal to T1 minus T2 by N. So
So you are not audible.
Okay, understood now?
Yes, sir, got it.
Yes, sir.
So can you please repeat what you said? You were not audible.
Sorry, repeat which part, beta?
So that last part, T1 minus Tp by x from there
So
on.
see, we are applying this concept that delta T by delta x between any 2 points is equal to the overall temperature difference divided by the overall length. Okay. So now for this is one point I'm considering. This is one point I'm considering. So here to here, what is delta T? It is T1 minus Tp. That is my delta T divided by delta x is directly this distance x. So this should be equal to T1 minus T2 divided by L. Understood?
Yes, sir. Got it.
Now you substitute the value of x as 2 meters, okay, and T1, T2, and L as given. So you will get the unknown temperature at the point P. Okay, so this is all there is to heat conduction. Okay, simple formula and simple concept. Okay, but yeah, we will see that there are few variations in types of questions, like combination of conductors can be used, or for example, we can have a situation where the area of cross section of the conductor is not uniform, so we have to use some kind of integration kind of thing. But that is like variation problems. The basic concept is this much only, that at steady state there are two equations that we can write for an isotropic uniform conductor. One is for the uniform rate of heat conduction and second is for the uniform temperature gradient. Okay, so we'll conclude today's session here today, people, and tomorrow we'll continue with some more examples of conduction, and also we will clear some more doubts from the earlier thermodynamics part. So that's it for today's session, people. Thanks for attending. Wish you all the best.
Sir, can we
Thank
start
you, sir.
doing
Bye.
the next chapter heat transfer from HCV?
Sorry, can you?
Can we start HCV
Yeah,
heat transfer?
heat transfer you can start. There are a lot of solved examples which are based on this conduction concept with combination of conductors, etc. You can start with those solved examples or directly in the exercise also you can start. Okay?
Sir, how many questions can we solve?
I will give you the homework tomorrow because okay, you do the first 6 examples from solved examples from HC1. Okay.
Okay, sir, sure. Thank you, sir.
Okay.
Awesome.